Chapter 2: Theoretical Foundations of Anti-Gravity. Anti-gravity transport hinges on a radical idea: manipulating gravity itself. But to engineer the future, we must first understand the present and the limits of our knowledge. This chapter delves into the physics of gravity, from its classical roots to the frontiers of modern science, and examines speculative mechanisms that could one day make anti-gravity a reality. For engineers and innovators, this is where theory meets possibility. Gravity in physics. The basics: gravity is the force that pulls masses together, but our understanding of it has evolved dramatically over centuries. Newton's law of universal gravitation. In 1687, Isaac Newton described gravity as a force between two objects proportional to their masses and inversely proportional to the square of their distance. This law explains why apples fall and planets orbit, but it's a description, not an explanation of gravity's true nature. Einstein's general relativity. In 1915, Albert Einstein revolutionized physics by framing gravity not as a force, but as the curvature of space-time caused by mass and energy. Massive objects like stars warp space, and smaller objects follow curved paths like marbles rolling on a stretched sheet. This theory has been confirmed by countless experiments, from gravitational waves to the bending of light. Quantum gravity. While general relativity governs the large-scale universe, quantum mechanics rules the subatomic world. Uniting these two pillars into a theory of quantum gravity is one of physics' greatest challenges. Such a theory could unlock new ways to manipulate gravity, but it remains elusive. Why it matters. Engineers need a solid grasp of these concepts to appreciate the scale of the challenge. Anti-gravity would require not just bending the rules of physics, but potentially rewriting them. Hypothetical mechanisms for anti-gravity. Anti-gravity is speculative, but several ideas from physics and science fiction offer tantalizing possibilities. Exotic matter and negative mass. In theory, matter with negative mass would repel normal matter, creating an anti-gravity effect. Imagine a vehicle equipped with negative mass components that push against Earth's gravity. However, negative mass has never been observed, and its existence would challenge our understanding of energy and momentum. Negative energy. Einstein's equations suggest that negative energy density could create repulsive gravitational fields. This concept underpins the Alcubierre drive, a hypothetical faster-than-light propulsion system that contracts space in front and expands it behind a vehicle. While intriguing, generating negative energy in meaningful quantities is far beyond current technology. Manipulating space-time. General relativity allows for space-time to be warped in ways that mimic anti-gravity. For example, a sufficiently advanced civilization might create artificial gravitational fields, or gravity shields. But this would require control over immense amounts of mass or energy. Think black hole level densities. Why it matters. These ideas, while speculative, provide a framework for innovation. Engineers can draw inspiration from them to explore new materials, energy sources, or field manipulations that could approximate anti-gravity effects. Current theories and models. While anti-gravity remains theoretical, several areas of research push the boundaries of what's possible. Particle physics and the Higgs field. The Higgs boson, discovered in 2012, confirmed the existence of the Higgs field, which gives particles mass. Some theorists speculate that manipulating this field could alter an object's gravitational interaction. However, this is purely hypothetical and would require technology far beyond our current capabilities. Cosmology and dark energy. Dark energy, which drives the universe's accelerating expansion, exhibits a repulsive effect akin to anti-gravity on cosmic scales. Understanding dark energy could provide clues for creating localized anti-gravity fields, but translating this to practical applications is a distant dream. Fringe theories and experiments. Some researchers explore alternative gravity models, like modified Newtonian dynamics, which tweak gravity's behavior at large scales. Others investigate electromagnetic gravity coupling, inspired by claims of electrogravitics from the mid-20th century. While these ideas are controversial and lack empirical support, they fuel creative thinking. Why it matters. These theories, even if unproven, challenge engineers to think outside the box. Innovators might find ways to test or adapt these concepts, leading to breakthroughs in propulsion or energy manipulation. Scientific challenges and gaps, anti-gravity faces monumental hurdles, rooted in both theory and practice. Energy scales. Manipulating gravity requires energy densities comparable to those found in black holes or the Big Bang. Current technology is nowhere near capable of generating or controlling such power. Quantum gravity. Without a unified theory of quantum gravity, we lack the tools to understand gravity at the smallest scales, where anti-gravity effects might be engineered. String theory and loop quantum gravity are promising but incomplete. Experimental limitations. Testing anti-gravity concepts is nearly impossible with today's instruments. For example, detecting negative mass or negative energy would require sensitivities far beyond current particle accelerators or telescopes. Theoretical paradoxes. Many anti-gravity ideas lead to paradoxes, like time travel or violations of causality, which suggest they may be physically impossible. Engineers must grapple with these constraints while seeking loopholes or alternative approaches. Why it matters. Acknowledging these challenges is crucial for setting realistic expectations. Innovators can focus on incremental advances like improving energy efficiency or exploring new materials that might one day contribute to a larger breakthrough. Conclusion: anti-gravity transport is a bold vision, but it's grounded in the same scientific curiosity that led to flight, space travel, and quantum computing. While the theoretical foundations are complex and the challenges immense, they are not insurmountable. For engineers and innovators, this chapter is both a primer and a call to action, to push the boundaries of physics, to experiment with new ideas, and to imagine a world where gravity is no longer a limitation, but a tool. Next steps. In Chapter 3, we'll tackle the practical engineering hurdles, energy, materials, control systems, and safety that stand between us and the dream of anti-gravity vehicles.